Okay, let's dive right into this explainer. Picture this. We're pushing deep into the heart of a Siberian winter with a military convoy. Out there, the cold isn't just something you throw an extra jacket on for. It is an absolute life-or-death threat. So today, we're looking at the heavy metal and the genuinely ingenious engineering it takes to actually survive the deep freeze.
Minus 50 degrees Celsius. When the thermometer actually drops that low, extreme cold isn't just weather anymore. It literally transforms into a brutal operational constraint. At minus 50, the environment is aggressively fighting against both human existence and the machinery. Everything changes, and your margin for error, it completely drops to zero.
I absolutely love how perfectly this quote captures the reality of it. It's an operational constraint that turns every piece of steel into a weapon against the very humans trying to use it. Think about the truck's cargo bed for a second. It's essentially a giant metal box, right? Within minutes of exposure, that steel matches the lethal temperature outside. Moving air circulates freely, and within hours, you aren't just shivering. You are completely losing the dexterity and concentration you need just to survive, let alone do your job.
So let's jump to section 1, the agitation. And here, we're looking at the false solution of the engine. Because when most of us think about staying warm in a vehicle, we naturally assume that massive diesel engine under the hood is our built-in furnace. It seems like the obvious, most intuitive solution. Just run the engine, right?
Well, actually, relying on engine idling is a completely false solution in the deep Arctic. Think about it. Idling a massive, heavy-duty diesel engine for 10 hours straight just to keep the cabin, somewhat tepid, it's incredibly inefficient, it burns through your precious fuel reserves, causes massive wear and tear on the engine, and honestly, it's just highly impractical when you're completely isolated in a frozen wilderness. You need something vastly more specialized.
Which brings us to section 2, the solution. Enter the OV95 autonomous heater. Soviet engineers totally bypassed the whole engine problem by creating a piece of pure Arctic life support. It's a fully autonomous, fuel-powered heater, and the most famous example of this is the OV95 unit. This was a total game-changer. We're not just talking about some extra heater core hooked up to the engine block. No, this was a completely independent system. It smartly ran right off the truck's primary diesel fuel, so you didn't have to lug around a separate fuel type. But here is the kicker. It could function flawlessly even when the main engine was totally shut down and dead silent. It gave you guaranteed heat without the massive fuel penalty of an idling truck. Now, if you look at historical photos of a Soviet-era ZIL or KAMAZ truck, you're going to immediately notice these strange, vertical metal units bolted securely to the outside of the vehicle. Sometimes they're wedged between the cab and the cargo bed, or even sticking right up above the roofline. At first glance, it looks totally unconventional, almost like a complete afterthought just slapped onto the exterior, right? But here's the crucial point. That external placement wasn't an accident at all. It was driven by deep, survival-based logic, because in a minus 50-degree world, aesthetics literally do not matter. By keeping the heater bolted to the outside, engineers made sure it was easily accessible. Imagine trying to tear apart a dashboard to fix a broken heater core in minus 50-degree weather. It's impossible. This design meant you could service the unit quickly right there in the field, keeping people alive. All right, section 3, the mechanics. Safe heat, no fumes. The challenge here is massive. You are actively burning diesel fuel to create fire, and you have to get that heat into an enclosed troop compartment without, filling that tiny space with deadly exhaust fumes. And this is how the heat exchanger actually pulls it off. Outside air enters the unit, and diesel burns to create a stable fire inside a totally isolated combustion chamber. Here's the absolute magic of it. The air you actually breathe passes through entirely separate internal channels. It soaks up the radiant heat right through the metal walls of the chamber. It's a completely clean, safe separation of flows. The breathing air never once touches those toxic exhaust gases before it's pushed right into the cabin. Moving right along to section 4, the strategy, bottom-up heating. Because once they generated that clean, safe heat, they had to figure out how to deliver it efficiently. The engineers specifically chose to feed this warm air in at the absolute lowest point possible, right at floor level. And as we'll see, there's a very specific, calculated reason for doing it that way. The reality of these rugged military vehicles is that they are not heavily insulated. Not at all. Most of the massive heat loss happens directly through the thin metal floor and the lower side panels. If you just blasted hot air at the ceiling, the people sitting inside would still have freezing feet, and that bitter cold would just creep right up their bodies. Pushing the heat from the bottom up directly combats that intense, localized heat loss. This bottom-up strategy, the floor-up effect, is incredibly efficient. Because hot air naturally rises, injecting it at the floor creates a uniform temperature distribution throughout the entire cabin. It physically pushes out and displaces those heavy, freezing layers of air that naturally settle at the bottom. By keeping the occupants consistently warm from head to toe, you preserve their mobility and, crucially, their operational readiness.
So, to put this into perspective, while sitting in the back of a GAZ 66 or ZIL 131 truck wasn't exactly a stay at a luxury resort, this autonomous system was highly effective. It could take a deadly minus 35-degree night outside and literally transform that raw metal interior into a highly survivable, remarkably comfortable plus 15 degrees Celsius. That is a 50-degree swing, and it's powered entirely by a simple, standalone metal box.
Let's zoom out a bit for Section 5, the engineering legacy. The philosophy behind the OV95 is exactly what allowed these brutalist, heavy-duty machines to confidently operate in conditions that would instantly brick a modern, heavily computerized vehicle. This right here is the core legacy. It's the absolute definition of Arctic life support logic. Heat the person, not just the machine. And you achieve that by prioritizing extreme mechanical simplicity and rugged autonomy over complex, fragile electronics. I mean, in a life-or-death situation, you definitely don't want a microchip deciding if your heater turns on. You want a simple mechanical fuel pump and a spark. That's it. What's really amazing is that this technology didn't just disappear when the Cold War ended. That exact same Arctic life support logic has steadily evolved. If you look at modern motorhomes, camper vans, or the sleeper cabs of long-haul semi-trucks today, they rely heavily on compact, quiet, highly refined versions of these exact same autonomous diesel heaters. This entire concept is just a beautiful reminder for anyone interested in design or engineering. When you are pushed to the absolute limits, when you're literally trying to survive the deep freeze or the most extreme environments on Earth, the best engineering isn't the most complex system, it's always the most reliable one. Pure, unwavering reliability will beat sheer complexity every single time. So to wrap up this explainer, we've seen how Soviet engineers kept heavy machines moving through Siberian winters. But I want to leave you with this to chew on. When you are faced with extreme conditions, whether that's in your work, your systems, or just your life, how do you adapt? What's your personal strategy for building extreme reliability? Keep that in mind next time the temperature drops.